A very good afternoon to all. I, Shashankian, Assistant Professor in the Department of Computer Science and Engineering and the Faculty Coordinator of Wireless Internetworking Research Group, extend a heartfelt welcome you all for the AICTE sponsored International Colloquium on Recent Trends in Computer Science ICRTCS 2, which we are going to present a talk on digital twins for the trustworthy autonomy. Welcome anything that comes to you, but do not long for anything else. It gives me immense pleasure to welcome today's speaker, Dr. Francesco Flammini, sir, Professor of Computer Science and Head of Cyber Physical Systems, Chair of IEEE SMC Tech, and Committee Homeland Security, Rome, Italy. I even take this opportunity to welcome our beloved Principal, sir, Dr. B. Sadashivegowda, sir, in his absence. Welcome you, sir. I even take this opportunity for welcoming our beloved head, Dr. Ravi Kumar, sir, Professor and Head Department of Computer Science and Engineering. Welcome you, sir. I also take this opportunity in welcoming Dr. Janavi ma'am and Dr. Gururaj, sir, the coordinators of Wing, VVCE Mysuru. Welcome ma'am and welcome you, sir. I welcome all the deans, heads of various departments, faculty members, non-teaching staff of VVCE Mysuru. Welcome you all. Last but not the least, I welcome all the participants of various colleges, industry personnel across the globe. Welcome you all. Now, finally, the time has come to introduce our guest speaker, Dr. Francesco Flammini, sir. He obtained his honors in Masters in 2003, doctoral degree in 2006 in Computer Science and Engineering from the University of Naples, Federico to Italy. He is currently working, he is also working as adjunct professor in cybersecurity, software engineering, data science. He has supervised and co-supervised 4 PhD students. He is also an IEEE senior member and the chair of IEEE SMC Technical Committee on Homeland Security. He has authored and co-authored more than 100 scientific publications. He has served as the chair, invited speaker, steering program committee member for several national and international conferences. And Sir is also the member of many reputed organizations like European AI Alliance, FME, that is Formal Methods Europe, and many more. Sir's research interests include dependability, fault tolerance, resilience of real-time embedded and autonomous systems, mobile-based engineering and multi-formalism, stochastic modeling, UML, Petri nets, Bayesian network, Markov chains, fault trees, reliability block diagrams, and many more. Sir, once again, on behalf of the Department of Computer Science and Engineering, Vidyavardhaka College of Engineering, Mysuru, I extend once again a heartfelt welcome to you, sir. Now, I request Sir to take over the session.
Thank you very much for your kind introduction. So I will not steal your valuable time presenting myself, because you already presented me with this nice, very good presentation. So just say that I am involved in several IEEE initiatives, and you will see in this title slide, one is the IEEE SMC, System and Cybernetics Society, which I'm a member at large of the Board of Governors. And I'm also member of this other initiative that is about digital reality, which has a strong focus on the concept of digital twins. So my objective for this presentation, for this guest lecture, is to introduce the link between digital twins and trustworthy autonomy. So we know that it's very, very important, extremely important, if not essential nowadays, that autonomous systems, such as self-driving vehicles, are considered trustworthy. So trustworthy is a general concept that includes the concepts of safety, dependability, reliability, and security. And it is a word, an attribute that is mostly used for intelligent systems, because autonomous systems are also considered smart or intelligent systems. So this is extremely important, no doubt about that. But how digital twins could support, could help to achieve trustworthiness in autonomous systems, this is something that we will see in this talk. But let's start from the concept of smart X applications in smart cities. Smart cities are a central concept nowadays, and they include basically all smart X applications. We can include factories, industries, even though they are mostly outside cities, but they are considered within the concept of smart cities. So you have smart manufacturing, intelligent factories, and all the other smart X applications that you can easily imagine, such as smart health, smart grid, which is also one very important and crucial application. Then you have smart buildings, smart homes, more in general, and smart transportation. So autonomous vehicles, for instance, autonomous cars, self-driving cars are part of smart transportation. How you enable this? There are some technologies that are considered enablers of smart X systems. Without those technologies, you cannot have smart systems. One technology, one central technology and paradigm, I would say nowadays, is the paradigm of the Internet of Things. So all devices in these smart buildings and smart transportation systems are connected to each other, and they transmit a big amount of data. This data can be really valuable because based on this data, you can make your systems more intelligent and smarter. However, you need mechanisms to collect and analyze this data because data is a high cost. So if you only have data but you cannot analyze this data, then it will be expensive and with no return on the investment. Instead, if you can analyze this data, make your systems more intelligent based on the data that you collect, then you're creating really smart systems. And it is a matter of fact that the number of connected devices is has an exponential growth over the year. So we will have more and more connected devices in the future. So this is a big advantage, a huge potential, but also poses a lot of concerns about the security of data, the privacy of data, for instance, and the trustworthiness of the whole systems that use those data. So you have these grand challenges. I have just summarized some of the grand challenges with a focus on trustworthy autonomous systems. First of all, let me say that nowadays autonomous systems also belong to the class of cyber-physical systems. That is to say, they have both a cyber and physical component. So if you have a self-driving vehicle, you have the mechanical, electromechanical part, but you have also the control systems and the software that is increasingly important. So these systems are ubiquitous and pervasive. They are in all aspects of our everyday lives. They are becoming increasingly smart, intelligent, and autonomous. There is a huge focus on these attributes nowadays, especially based on the progress on artificial intelligence and machine learning. But at the same time, if they are critical systems, I mean, their failure can have consequences on the human beings and the environment. They must also be reliable, safe, and secure, and possibly certified according to international standards. So how you manage all these aspects at the same time? Complexity, because they are growing in size, distribution, heterogeneity, because they're made up by very diverse hardware and software components, and all the uncertainties that are given by the environment, because you cannot predict 100% the environment in which those systems operate. And also there are several uncertainties coming from the system themselves, how they are designed. So if you're using artificial neural networks or other machine learning approaches, you don't have a full white box. So some aspects of how the system will evolve over time are not perfectly predictable. And so you have several sources of uncertainty. So these are the grand challenges nowadays. So one concept that is very important to make a structured and systematic approach to trustworthy autonomous system is the concept of resilience. The concept of the resilience, first of all, is derived by the concept of dependability. These concepts have been formalized more than 15 years ago by a group led by the scientist that was named Jean-Claude Laprie. Now he passed away recently, unfortunately, and he defined dependability, system dependability, as an integrated concept, including dependability attributes, dependability threats, and dependability means. Among dependability attributes, you will find availability, reliability, safety, confidentiality, integrity, and maintainability. Regarding threats, you have faults, errors, and failures. Finally, regarding means, to ensure dependability, you have fault, error, and failure prevention, fault, error, and failure tolerance. Then you have removal and forecasting. Forecasting is normally based on models, mostly stochastic models, but also model checking, theory improving, all the models that can support assurance that your system is safe, reliable, and secure. Now, resilience, we say that is derived from dependability. And resilience is basically the persistence of dependability when facing changes. So you have several possible definitions of resilience, but the shortest one is the one that I like more. It's the third bullet point in this slide. So basically, it's dependability in presence of changes, because those changes, for instance, software upgrades that you can have in self-driving cars, or changes in the environments, those changes, they cause uncertainties. And this is one of the grand challenges that I have mentioned in my previous slide. That one common concept in the field of critical system is the concept of risk, how it is this concept related to the concepts that we have already introduced before. So risk, in its most common definition, that includes both qualitative and quantitative aspects, is a combination of a probability of threats. So we summarize in this slide with P, but it could also be represented by frequency of threats. So how many threats you expect in 1 year or in 1 unit of time, regardless that is 1 year, 1 month, or 1 hour. Then it is multiplied. So the second factor is the vulnerability of the system against the threat. And this is normally considered a conditional probability. So what is the probability that the threat is successful given that you have that threat happening? So in a perfectly protected system, you have zero vulnerability. So you can have any threat, but you will be 100% protected against those threats. In real system, it's not like that. I mean, many threats, maybe you can mitigate some threats at the same time or at runtime, but you will have some effects. And these effects are summarized by the D, that is the initial of damage. So sometimes it's D or sometimes it's C, because C is the initial of consequences. And it basically measures the effects of the threat on your system. This risk is represented together with some more quantitative metrics, such as the mean time between failures, and those failures can be both reliability failures with no effect on safety, or you can have also safety failures. So it could be mean time between accidents, actually. It depends on the failure mode that you are considering. In a complex system, you can have many failure modes. And then one other metric that is related to this MTBF is the hazard rate. So in this case, in the hazard rate, you're just considering the hazard, so failures that can have consequences on human beings or the environment. So you're concentrating on safety critical systems. So you have some ways to measure those metrics clearly, and these thresholds and these numbers are given by reference international standards. But how you do that? I mean, if you have a complex critical system, it's really very difficult to measure the hazard rate or the mean time between failures. So in order to do that, you need models. All engineering is based on models, and you have several approaches. So in this diagram, you have one view in which model-based engineering, so you have the largest set, MBA, model-based engineering, that includes model-driven engineering, that is subset that uses UML, basically the unified modeling languages, so diagrams and views of the UML. Then you have model-driven, more specific model-driven design and model-driven architecture. So you're going more in depth into the hardware and software co-design using these approaches. And this is the only way in which you can ensure the dependability, resilience, and we will say the trustworthiness of complex cyber-physical systems and autonomous systems. But in practice, what you will do, you will build models. And one way to build models that are easy to manage to a certain extent is to use multi-paradigm modeling. What does it mean? Multi-paradigm modeling basically includes multi-formalism. So you use different modeling formalisms depending on the level of abstraction and the nature of the subsystem that you want to model. Then you use also abstraction. So it's very important to build models that are not too complex. So you need to model the important things that you need for your system, and you should make models as much simple as possible, but not too simple. So this calibration of fine-tuning of the level abstraction is very important. And it's the ability of the modelers. It's a creative process. And then you have meta modeling. That is the third pillar of multi-paradigm modeling. Meta modeling means modeling formalism itself. So basically, you create modeling formalism. In order to create modeling formalisms, you use models. So this is the meaning of meta modeling. For instance, domain-specific languages. You can have languages specific for a certain domain. You can create using meta modeling, and some domain-specific languages are easy to build using, for instance, the unified modeling languages and its extensions like the CSML, for instance. So this is one way to manage the complexity of real systems by splitting them into abstraction layers and into subsystems using diverse modeling languages on these approaches, the modeling approaches that I have just mentioned. In the end, if you build appropriate models and you can check those models, you can use those models to measure. So you have for sure some stochastic aspects integrated into the models. For instance, you use stochastic battery nets. You can measure the things that you need to measure, and this is essential to approve, to certify your system against international standards. This is essential, especially with safety critical systems. But it could be worse. Why? Because, and this is what's happening nowadays, you don't have fixed systems that don't evolve over time. That happened in the past. For instance, I worked many years in the railway industry, and if you build a railway system, it will not change perhaps for 20 years, 30 years. It will remain the same until you will decommission the old system and install a new one. And also the environment is a controlled environment with no modifications in the environment. So everything is perfectly controlled and predictable. But nowadays we are entering a new era in the computer science and engineering world. We are entering the era of autonomous systems and artificial intelligence and machine learning that also apply to critical systems. I mentioned several times self-driving cars, but you can have self-driving planes, self-driving trains, and heavy machinery in industry that is autonomous. All these systems that are autonomous and operating critical environments together with humans, for instance, cobots, industry robots working together with humans, they can also represent a threat, a risk for the humans if they have a malfunction. So again, for the self-driving vehicles, you have several levels of autonomy. This is very important to consider the level of autonomy, because I mentioned in the beginning, in the title of this lecture, autonomous systems, but not all systems have the same level of autonomy. Most of the systems that we have nowadays have a limited level of autonomy, and this is especially important for critical systems because we are not yet able to certify that those systems are safe in all operating conditions. So this simple fact prevents us to make a fully autonomous critical system in most domains. Maybe in military domains, in special domains, you could have a fully autonomous system, even in critical domains, because they have different norms. They don't need certification in civilian environments. But in 99% of the environments, I would say, such as the urban environments, you cannot operate a full autonomous vehicle that is critical, because that could kill a person if you don't achieve certification against international standards. That means that you have to demonstrate that the system is safe in all operating conditions. Nowadays, we are not able to do that. So you need the driver to put hands on the steering wheel and control the system. But in the future, we expect, I don't know if this will take 5 years, 10 years, 20 years, or 100 years, nobody can say. So some are more optimistic about that. Some believe that it will never happen. But I think the truth is in the middle. We will sooner or later achieve at least a high level of autonomy, in which the driver will be there just to supervise the system, possibly. But that needs a lot of work on and understanding of how machine learning and artificial intelligence work, and how you can make safe artificial intelligence and white box or explainable machine learning approaches. This is especially important considering that you could have evolving threats, new threats that you didn't have with traditional systems. So for intelligent systems, you not only you have limited predictability due to the intelligence, so evolution, that are all positive aspects, but also limit the predictability of those systems. But you should add to that you could have new threats. For instance, there are some properties of neural networks in which if you add a certain kind of noise on an image, you can change the perception of that image for an autonomous system. So from one animal, in this example, in this slide, you have a gibbon and that is completely different, clearly, from a panda. It's a completely different animal. But if you overlap this noise to a panda, and a human will continue to recognize the animal as a panda, but the machine will recognize the panda as a gibbon. So this is something that cannot be considered as very critical. But if you think that instead of an animal, you could have a road signal. Okay, so for instance, you have a stop signal, and you can someone could change that the perception of that stop signal for the self-driving car as an unlimited speed limit. That can cause an accident. A person could die, and you can do that very easily if you overlap one image, project one image on the signal. So imagine how many threats, new threats could happen in the future if you consider these properties of neural networks, new properties and new threats that could threaten intelligent and autonomous systems. So basically, what you need to do is to build intelligent systems that are also trustworthy at European level. But this holds for the whole world. This is just an example. In Europe, they have worked on some ethical guidelines for trustworthy artificial intelligence, and there is a working group defining white papers on trustworthy AI. And trustworthy AI basically is, as you can see in this image, in this slide, is at the intersection of an artificial intelligence that is robust, so is as much as possible tolerant to threats. It should respect all the applicable laws and norms, so it should be lawful, in one word, and also should be ethical. So when there are some dilemmas, as we call them, in which a self-driving vehicle should decide whether to save the driver or to save the pedestrian, for a human, it is more natural, or it is a problem that rarely happens because you have to take a quick decision, and people normally don't have much time to think about that. But autonomous systems, they can take this decision very quickly, and so you have to program them to have a wide code in the system to decide when they have to decide whether to save passengers or pedestrians, what is the best choice, and this opens the discussion to several ethical problems that don't have an easy solution. But in order to have a control over artificial intelligence, you need to have artificial intelligence that is explainable. So explainable artificial intelligence, that is one of the challenges that you have with artificial intelligence nowadays, is essential for autonomous systems. So with, for instance, deep neural networks, it's very difficult or nearly impossible to predict how the network will evolve over time if it will continue learning over the time, over the years. And this is not acceptable by traditional safety critical standards. I remember when I worked with the railways that it was forbidden to use neural networks in the control of trains because it was something that you could not predict, and so you could not demonstrate that the system was safe in all operating conditions. So having a system that is explainable, even AI can be explainable. There are some approaches, for instance, probabilistic approaches with Bayesian networks that are inherently more explainable compared to neural networks. Then you could certify those systems against international safety standards. But let's move on how you can use digital twins in order to achieve the objective of trustworthy autonomous systems. So basically, you start from the concept of autonomic computing or self-adaptive systems. And this concept has been elaborated in relatively recent times by IBM. IBM started this with this white paper on autonomic computing, introducing this so-called MAPE-K loop. So MAPE stands for monitor, analyze, plan, and execute. So it's sort of supervisor that you have over another system that monitors the system and takes the most appropriate countermeasure based on a knowledge. So this is very, if you think about that, this is very appropriate for intelligent systems which have some knowledge that should be as much as possible explainable if we want to have explainable AI. And think about this, and we will see how this can be integrated in the concept of digital twins. But before moving to that, let's mention how you can have this MAPE-K loop implemented in a easier way if you have a cyber physical system and you want to detect and recover from failures. So one approach that we implemented, my research group implemented in the past, is this based on the collection of events from the real system. Then you can use these events to detect threats and recovery from threats, and this is the easiest, the shortest path. But you can also have these events, you can use those events to increase your knowledge. So feed a troubleshooting repository, then adapt the system and try to prevent future threats. So based on this knowledge that you can get from the system itself and from the cloud, from internet, from other similar systems. So this is a simple implementation of the MAPE-K loop in a customization of the MAPE-K loop to troubleshooting of cyber physical systems. More in general, this approach would enable the concept of self-healing. So you will have in the future systems that could repair themselves. It's not only about repairing, so it's something that is broken and you want to repair, but it's something that those systems could adapt to recognize some faults or errors and correct them. So it's an evolution of fault tolerance to some extent using modern techniques such as artificial intelligence. So artificial intelligence and machine learning can be used to automate systems, to make self-driving cars. So that is the main objective, but it can also be used to make self-driving cars self-healing. So to recognize if there is a fault, error, or a failure, and to automatically recover from those conditions and malfunctions. But now, finally, we come to the concept of digital twins. I think that most of you have read about digital twins. Basic definition of digital twins is a very detailed model of the reality. So you imagine a CAD or CAM, computer-aided design, computer-aided manufacturing view of these 3D models of the reality. But in practice, nowadays, people are using digital twins at different levels of abstraction. So it could be a very detailed model, could also be just a runtime model. It could be very detailed or not very detailed, or just detailed for a specific prediction that you have to do. So if you want to predict performance, you have one model. If you want to predict reliability, you can have one other model, and you can possibly integrate all these models. But digital twins, in the way that we will consider in this presentation, is a runtime model. So it's a model of the reality that is continuously executed at a runtime, getting data from the real world. So it's not the model used at design time. If you want to build a new system, you need models to predict and to evaluate the system that you want to design, to develop. But the concept of digital twins moves models basically from design time to runtime. So you keep those models alive, and you can make some predictions using those models while the system is operational. So now it's becoming a little bit complicated, but I try to simplify as much as possible. If you want to use digital twins as runtime predictive models, you can make an easy representation. If you look at the models at the left, it's simply flowchart. And you use this flowchart to basically control over the time continuously if you have achieved the dependability target that you wanted to achieve. Okay, so if you have achieved the dependability target, so you can continue executing the system. So you have a self-driving car. Okay, so you're continuously controlling that everything is okay, and And you do this check continuously using this monitor. Imagine this digital twin used as a monitor of the real system. But if not, then you have to compute some plans or to elaborate some reconfigurations options in order to mitigate some faults and have the system continue operating in a new configuration. So it will be a fail-safe operation, let me say. But if that is not possible, then you have to stop the car. You have to tell the driver, okay, I cannot drive safely given that I have these faults, and you have to take control of the car if you have a manual operation, if you have a driver sitting there as you have today. And so the autonomous system will switch to manual operation. So this is basically the concept. And this same representation, if you look at the right part of this slide, the same representation you can have with a state chart, okay, in which you can have single minor faults or multiple minor faults or critical faults. Depending on those faults, you have to decide whether you want to shut down the system. For instance, with trains, you command the emergency braking and the train will stop. With cars, you can have a switch to manual operations. With planes, you should have backup systems. So if you have pilots on board, you will switch to manual operation. If you don't have pilots on board because you have drones, autonomous flying vehicles, then you should have some backup systems. If the main system fails, you will have remote control or another system that brings the drone back to the station. So in the future, what in my view, we will have a hierarchy of digital twins, basically integrating the MAPE-K loop that in turn will control the system. So let's start from one part of this diagram so it will be easier to read and understand. So you have some physical assets. So imagine a smart factory, a smart city with the IoT devices collecting data. This data is monitored by a digital twin through the MAPE-K autonomic manager, will be analyzed, and based on the knowledge, a plan will be prepared and executed on the system. So this is a continuous loop, the MAPE-K loop, in which you monitor the system and plan appropriate countermeasures. So if you have a network of these systems at the edge level, okay, so at the lowest level, you can have a digital twin for each. It's not mandatory to have a digital twin for each of the subsystems, but you could have. And you could have higher level in the hierarchy, digital twins at the fog computing level. So it could be local area network, campus area network, metropolitan area network. And then you have the top level, the real cloud, in which you have a data center that can be in the other part of the world that analyzed all the data, and you need a lot of computing power. So when you move to the cloud, you can collect more knowledge, and this is very important for machine learning. You can have more computing power, storage, and this is normally more cost effective because it's concentrated in a single location instead of replicating a lot of hardware, having more redundancy. But at the same time, if you move from the cloud to the edge, you have more confidentiality because data is not shared, especially if you have data that is confidential. Often it's not possible to send this data over the internet and have data centers in locations which in other countries from which you don't have any control. Also, if you operate at the edge level, you have a quicker response time because you don't have the latency of data that are transmitted over the internet. And you can have more autonomy also. And this is quite obvious because if you lose the connection, so if you have a self vehicle, self-driving vehicle, and you don't have any connection to the internet, because it could happen that you don't have any connection for some reasons, then you have local autonomy. So the system is self-healing, for instance, even if it has no connection to the internet. So this is a balance between the edge level and the cloud level. So both has some advantages and disadvantages. But let's make a real-world example to understand how this works, can work in practice. And we wrote this paper recently. Last year, we published this paper with my fellow researchers, in which we have explained this concept. We didn't refer to the concept of digital twin, but in practice is acting as a digital twin. And it is based on a case study of vehicle detection. So it's more in general, it's event sensing. So you have a system of sensors that are meant to detect one event in the real environment with some levels of redundancy. So you don't use one sensor, but you use more sensors, and diversity. So these sensors are different from each other. They use different technologies. This is very important because they don't have the same ways of failing. So coming back to the vehicle detection, you see that you have a camera with a smart camera with intelligent vision algorithms that can detect a vehicle, but you can also have many other technologies. You have a summary on this, the right part of this slide. You can have microwave, infrared, ultrasonic, a lot of technologies that can be used to detect an event, detect, in this case, a vehicle. And it could be used in practice in mixed traffic intersection, which you have tramways and cars, for instance, and you need to command a signal, operate a signaling system of the tramway, consider the presence of cars and other vehicles on the streets. So this is one real-world case study, and what we did, we customized basically the diagrams that I showed before. So the flow chart on the left and the state chart on the right, they have been customized on the specific case study of vehicle detection. But it's basically the same approach. It is only more detailed based on the requirements of the standard. So you have safety critical standards that tells you how much safe the system must be. So you want to evaluate the hazard rate of the system. So these real-world metrics in order to demonstrate that your system is safe in all operating conditions. And what you do in this case, you operate on the sensor reputation. So this is very important in artificial intelligence. Such as for people, you trust people when they have a good reputation. Okay, so if people, you can trust people, you know that you can trust people if they provide you with correct advice and information. The same holds to sensors. So if you have sensors that agree with the others and have a low rate of failure, so you trust more those sensors. Otherwise, you reduce the level of trustworthiness of the sensor. That impacts on the level of trustworthiness of the whole system. So this is basically the concept that you can implement. And in order to do that, we used an explainable AI approach. So we used extensions of Bayesian networks. So Bayesian networks was the basic formalism, that is a probabilistic modeling formalism. We extended with the time varying aspects and dynamic Bayesian networks. So we used basically an extension of Bayesian networks in order to model the system. And you can have a summary in this slide of what we proposed and demonstrate that could solve the issue in this specific scenario of event sensing. So you have, basically in this slide, you have the MAPE-K loop. You see monitor, analyze, plan, and execute. And the shared knowledge is in the center and is represented by dynamic Bayesian networks. As I said, they support explainable AI because it's something that you can see how it works. You can clear view of how the nodes are connected to each other, and the conditional probability tables that are associated to the graph in order to have a full representation of the Bayesian network model. This is used to basically drive the adaptation of the reputation of the sensors and exclusion mechanisms in case sensors are not considered to trustworthy, then you want to exclude the sensor that you cannot trust. And okay, this is very detailed and it's taken from the paper, but basically, to summarize, we were able to demonstrate that the system could be reconfigured if you have enough sensors and some of those sensors failed or could not be considered trustworthy. We could use this self-adaptation approach. We could reconfigure the system in real time in order to use a different configuration of the sensors, different sensors, in order to achieve different levels of safety integrity. So this is the SIL, SIL, safety integrity level is something that is used in the reference safety standards. And basically, we use this matrix to demonstrate. These metrics are associated to some numbers. So for each safety integrity level, you have to demonstrate that the probability of failure per hour is lower than a certain threshold. See how little these numbers, these probabilities are. 10 powered minus 9, for instance. It's the maximum level of safety criticality. And this is a novelty. I mean, nobody has done this before, to have an approach based on dynamic Bayesian networks to measure or reconfigure the system in real time and demonstrate in real time. So runtime, while the system is operating, that is still safe if you can have a configuration to achieve the safety targets that you want to achieve, or in some cases you can come to the conclusion that is you don't have a configuration of the system that is safe enough, and in that case you need to switch to another backup system, as I said before, or you can have a fail-safe operation. For instance, you set the signal, tramway signal, to stop because you put yourself in the worst case in which a vehicle is always present. That is the worst case in which a vehicle is always there. That will completely stop the system, and it's for sure a safe shutdown operation. Not with all systems you can have a safe shutdown. As I said before, in many cases you must switch to manual operation, or you must switch to other backup systems. But in this case, for instance, you can put the signal to red to stop signal, and so in that case it will be safe. And then you have to fix the system, so to replace the sensors that were broken, or just to, in some cases, instead of replacing the sensor, you have maybe just clean the glass of the camera because it was dirty and things like that. So it could be a replacement of some sensors or some other maintenance operations on sensors in order to restore the system to its maximum level of safety that could be achieved. One more thing, one of the last things that I'm addressing in this talk is the use of process mining. This is a relatively new concept, and it has a huge potential, and it's basically more qualitative than quantitative. So the things that I said before were basically based on probabilities. So to demonstrate that the failure rate of the system is below a certain threshold of acceptability, that is especially important for safety critical systems. But you could have also a qualitative analysis of your system, and this could be done with process mining in combination with machine learning. So process mining basically provides a model of the system, how the system should operate, and allow you to detect any deviations from nominal behavior. So if this real system is behaving in a way that is not according to its specification, and you want to detect that automatically, you can use process mining for that. And you can also have some metrics. I mean, it's not only true, false, or black and white. You can have some nuances of non-conformity, and you can have a metric that is not a formal probabilistic metric, but is a metric that can be useful to measure how the system is complying to its specification, or if you have a small deviation from the specification or a big deviation from the specification. But this, I think it's very important to use in combination with the other approach, and could also be integrated in the MAPE-K loop to analyze and plan. And therefore, it could be integrated in digital twins to make autonomous systems more trustworthy. I will also mention and conclude my speech with this project that we are developing, and I'm the technical manager of. It's a European funded project about intelligent railways. It is, I think, the first project worldwide that addresses specifically artificial intelligence in railways. And I know that this is very important in most countries, including India, because you have a lot of railways, and basically in the whole world, people, they want to make those railways more modern using digital technologies. Well, with AI and machine learning, you can cover a lot of challenges. So it's not only autonomous driving. Most of the times I've mentioned autonomous driving, but it could also be smart maintenance, so to optimization of maintenance on vehicles. So with not necessarily safety critical maintenance, but all kind of maintenance to reduce the cost of operation of railways, reduce the staff. So save a lot of money with using intelligent techniques to support maintenance. And also one other approach that we are investigating in this project is traffic planning and management optimization. So that is also not considered a safety critical aspect, but it's very, very important to have a tool that is able to automatically analyze the situation of the traffic over a railway network and readapt the traffic in case of disruption, or trying to optimize the capacity of the networks. This could also be effectively supported by artificial intelligence. Okay, so that's all. I hope I was not too late with the timing. Thank you for your kind attention, and I'm available for to answer your questions.
Thank you so much, sir, for your wonderful session. Dear participants, if you have any questions, you can put it in the chat box. We'll take that one.
Thank you so much, Francis. It was a really good and insightful talk. I think we have a few questions from the participants. We can have a Q&A session.
So is there any way for me to read the questions, or you will read these questions to me?
No. The session chair will take over the questions. Okay. No need to worry. Yes.
Mm-hmm. Mm-hmm.
Dear participants, if you have any questions regarding the session, you can put it in the chat box.
I have one question, Francis. How does digital twinning, reinventing the innovations?
Sorry, can you repeat?
How does digital twinning, reinventing the innovations?
How this digital twin will innovate maintenance?
Innovations.
Well, I mean, digital twins are used in many domains nowadays, and they were born in the smart manufacturing domain mainly. So if you look at the history of digital twins, if you make a search in Google, the first attempts to use digital twins were introduced by big companies like General Electric. I think they mentioned digital twins for the first time. Then the NASA also used and wrote some papers about digital twins. And nowadays, after many years, digital twins are considered an essential aspect of operations and maintenance by all big companies, including ABB, Siemens. And now, while there is a huge interest in digital twins, I feel that there are not many real implementations of digital twins. I mean, there is a huge potential for innovation, but it seems that enabling technologies that we give for granted, such as the IoT, are still in many companies at an early state of development. So they have custom sensors and they have custom applications of digital twins that have been successfully working for operation and maintenance, for instance, in General Electric. But many other companies, they are mentioning approaches based on AI and machine learning, but it seems that we don't have many real-world examples and applications. So it's still one challenge, and the same holds for what I'm mentioning in this talk. I mean, I mentioned my view on how digital twins could be used to support self-healing in the autonomous systems, more in general, all systems based on IoT, so cyber physical systems with IoT sensors. But to make it real, this innovation real, it is not easy. And we are still missing methodologies, I would say, first of all. So for instance, I had a master student at Malardani University, and I asked her to work on a methodology to build a digital twin. So first of all, you have to understand what is your problem, what do you expect from the digital twin, how you collect your data, where you run the digital twin. So you have to answer a set of questions to support the building of your digital twin. So it makes no sense to say, okay, I have this system, I immediately start building a digital twin, because then you will not be able to take the decisions on the level of detail of the model, for level of abstraction, how the model is updated, what are the parameters that you need to take into account. So what I see is that many things are missing, but before all, it is missing a clear methodology, a shared methodology for building a digital twin. Probably there are some companies they have, but they are not sharing, so it's still considered an industry secret how they do that. And this is why it is very important to explore these research directions. Starting from more methodological views, so not very detailed on computer science, on AI and machine learning. So how you manage this innovation to introduce in your organization, in your company, the Internet of Things, storage of data, analysis of data, and digital twins that use that data to improve the way you operate, basically. So reduce the costs, make your company more efficient. How to do that needs methodological view, and then you need also technology experts, because doing machine learning is also very challenging. So it's really, I would say it's a cross-discipline problem that is not only within computer science and engineering, but also includes people being able to manage innovation, so innovation managers. I hope that I have answered
Yes,
your
perfect,
question.
perfect. You answered my question.
Sir, there is one question. Can you please recommend some research topics on this area?
Okay, good question. One I have just mentioned. It really depends on your background. I mean, because there are many research topics that I just said that are somehow related to digital twins and trustworthy autonomous systems. So it's a collection of challenges nowadays. Most of these are open issues. So the path towards self-healing systems and real adaptive systems is very long. So it's not something that you have today. So one, I've mentioned the methodology aspect on to guide engineers to build digital twins, and that is a very general one. I mean, it's more related to digital twins, regardless of the fact that you're using digital twins to support maintenance or to make your system more trustworthy or safer. And so if you have a broader background in engineering management, innovation management, maybe you want to address this approach. Instead, if you are a more low-level scientist, computer scientist, computer engineer, and you are familiar with AI and machine learning, I would say that one very interesting research topic nowadays is how you can use machine learning for cybersecurity. Now, I'm mentioning cybersecurity because it's the most common topic, but I would say more in general, cyber safety, cyber resilience, or cyber trustworthiness. Okay, so it's broader. It depends on how much you want to be specific. But if you stick on cybersecurity, which is the one that is most used nowadays, using machine learning for cybersecurity is a very current and hot topic. I have worked on the topic. I have some recent papers about using Bayesian networks and neural networks, even deep learning, to support cybersecurity and in cyber physical systems. I would say more in general, cyber physical security, because it not only considers cyber threats, but it would also consider physical threats. So sometimes you have strategic attacks. If you consider homeland security or the protection of critical infrastructures, you can have strategic attacks putting together physical means and cyber means. So that is one thing. If you have intentional threats, but even with the random threats, natural threats, so there is no one that intentionally wants to attack your system, but you're just unlucky. You can have an unlucky combination of physical threats and cyber threats, so malfunctions or flooding and earthquakes. I mean, anything that can be natural. And the combination of these threats creates big issues for your systems if you don't have effective recovery mechanisms for cyber physical defense, such as backup centers, business continuity plans, and disaster recovery, just to mention some that are quite common in modern enterprises. So using AI and machine learning for cybersecurity, I think it's very, very interesting and a hot topic nowadays. I could mention many, but yeah, I would limit my suggestion to these ones.
Sir, I think there are no more questions from the participants. On behalf of Vidyavardhaka College of Engineering and also from the Department of Computer Science and Engineering, I extend a heartfelt thanks for your valuable time for highlighting the topic on the digital twin security for the trustworthy autonomy. Thank you, sir. Thank you so much for joining with us.
Thank you for inviting me. It was a pleasure for me.
Thank you, Francis. Thank you so much for your great session on digital twinning, and we look forward for your future events and collaborations. Thank you so much. Bye. Take care.
Thank you very much. Bye bye. Have a nice day.